Hello, this is Bob Golding again at Senior Escalation Engineer at Microsoft Charlotte site, talking about page file map file madness part 2, where we go into the debugger and we actually look at some structures regarding shared pages. So in this particular instance, we have a page fault and we have what's called a Proto PTE. But before we get into that, I just wanted to mention a kind of a new PTE type, a prototype. It's called a protovad, which is actually gets filled in by memory manager. So when a page fault occurs, and it just tells it to go look up the translation in the VAD. Okay, the PTE can be zero. If it's zero, the PTE in a user address, MM will validate the page and be sure that we don't cause doesn't result in a protection fault because it's invalid, because invalid pages can have zeros in the PTE address inside the PTE array for invalid addresses. But if this is in there, this was filled in by memory manager at some point, this means, hey, it's valid, go look it up in the VAD. Okay? That's what that is, and it's relatively new. I just wanted to touch upon it a little bit. If you do run across it, when you're debugging, that's it. That's what it is. Um, so I just wanted to talk about that a bit. And now let's get into some of the page file operations about DLLs. If we look at this right here, we're taking a page fault, that logical address, and we went through the it was a cache miss. We talked about the TLB cache, and it forces the microcode to do a PTE walk. So it goes through this page, the down, and walks the different pages. They go down to finally get to the PTE. The valid bit was not set, so we go into the page fault handler, and we have to handle the page fault. Now, when we go through the page fault, since the valid bit is zero, the rest of the bits available for software use. And we go into the PTE and we see what's called a proto. Proto PTEs are used in shared files. The proto PTE is an address that's put in the user PTE array that actually points to where the PTE resides, this is actually a pool allocation called MMST. Now, in this this is where the information is stored about the DLL that we're faulting on the shared file. Usually we put the proto PTE in there if the page has been removed, from the working set for some reason, and we put the proto in there. So we take a fault, we go right to the PTE. Consider, for example, you have um, five processes sharing this page, and we remove the page from one of the working sets. We put the proto PTE in there so we could go back and just put it back into the working set again. That's an example of how this is used. So if you go to the proto, we see that this is the PTE that's going to be put into the user space. Okay, so this PTE will be moved into this PTE contents from the MMST will be moved into the PTE array, and the instruction will be retried. Okay, now you see that the execute protect bit is on, and in these in this area inside the MMST, which is this little area is called a subsection. We'll look at that in a minute. And since the execute bit is on, that means these are read write. Okay, so this is a data portion of the DLL. We'll see that in a minute. Okay, and as we go down, we see that we have a. Oh, we'll just go to this. This here is a good example. This here is a another page. Now this is another prototype PTE, or transitional PTE, I should say. And if you take the page number, we see this on the standby list. There's the PTE. So this page has been repurposed, okay? And if a page fault were to occur, we take it off the standby list and put it in the MMST, and then move the contents to the user PTE array, okay, to make it valid, okay? So this page has been repurposed. And right here, and if we look, this is the, say, for example, we want to repurpose this page. We want to take this page off the standby list and repurpose it. We have to fill the PTE in with the information to where to get the data back in the file. And this happens to be the subsection. We do that, and okay, this is the subsection, okay, and it has the protection. And since this is a data part of the file, it's read-write copy, so it's a copy on write. So what we're going to do, if we do write to it, we just make a copy of the page, and the user or the process that access the page will have its own unique copy. Okay, so we could even take a page fault, and we could go in a user PTE, have a Proto PTE that points to the original PTE content, which is actually the subsection, and go read the page in. Okay, so the pointers, the pointers that are in the MMFT actually, so the contents actually get put in the user PTE array, and then on the page we bumped the share count. Okay, so we want to see what. So if we want to see what file it is, we go to subsection, and get the control area. Control area is the first offset. This has been this way for a long time, but it is subject to change. If you do bang CA, which is a debugger extension, we can see all the subsections in the control area. The control area has information in the file, and this is the segment, and has the size of the segment, image info. Okay, it's information about, I guess, all the controlling subsections. Now, each subsection for a DLL maps to what's in the header. And these are all the section headers. Now, each section header maps to a subsection. The first subsection is page 0, which is 1 PTE, which is 1 page. The next one is 70, so if we go to the first subsection, there it is, 6F, so it's going to take 70 pages. It's execute read. And the one we were looking at was $data, and it was read write. Okay, so each one of these subsections maps to a section of the file. Okay, so let's take a look at. So if we do and we look at its VADs, when we talk about VADs, there's all the VADs. These are all the VADs for this particular process. Okay, and now all these VADs are mapped to executables, and this is ours right here. So this is the first page. Okay, and there it is, the first PTE. Okay, so that's its mapping, and that's physical page. Okay, so share count is 2. That means 2 processes have this mapped. Okay. Now, if we go to this logical address, there are the contents. And this is the physical address. So if we go to the physical address, see it's the exact same thing. Okay, so this is how shared pages work. And if we go to any one of these, and hopefully this maps out. I'd put this machine in memory contention. Okay, well this is execute protected. But if we go to PFN and look for the restore PTE, we see this is mapped 66 different places, but that means no one's written to it. I think this is read write. I think this looks like it's execute protected. It might be part of. I think it's read write, right? See, yeah, I think it's that's protection. So you do bang PTE, base 1, and there's a subsection, and it's read only. Okay, sorry, yeah, read only. It's a read only subsection execute protect. Okay, so I don't know what section it belongs to or how it's defined, but if we go back, there is there are all the subsections that map to that crypt DLL. Okay, so that looks like it's a read only. It's a read only section that looks like it's execute protected. Okay, so that works, and we can look at it. We can look at a VAD. And if we go to core, there's the starting VPN, virtual page number, ending VPN, and it's high, the high numbers, okay, because it's broken up. And so this is how the system knows how to map the file. So if you have to go look up the address in a VAD, it finds the VAD for this virtual address, and you have the subsection and the first prototype PTE, the last contiguous. So you have information about how to look up the file. Since you have the subsection, you could get to the control area, and the subsection describes how it's what the mapping should be. So what is this subsection? F0. Okay, I'm using internal symbols. So that's how it's laid out. That's the subsection. So that's a crypto. So that's the subsection that belongs to that file. So we go, what file is that? Did I get the right file? Do bang CA on that. You just grab that. Oh, okay, that's why. Do bang DH, and we can look at what section was the one I grabbed here. Grab the subsection off the right here. So what's that map to? Okay, so that's read only. So that's page 0. So that's uh, that's read only, execute protected. Okay, I tend to talk about the working set a bit. Working set's an array that's inside the operating system, and there's the page number, uh, the logical page number, and we use that to maintain pages to age pages, and if once a page reaches a certain age, it's not being accessed, depending on the memory, what's going on in memory. The memory could, if we're in memory contention or not, and what the situation, if memory's in demand or not, we will remove the page from the working set. When we remove it from the working set, we have to invalidate the PTE to fault it back in again. That's all a working set is. It's not. And all it is an array, basically, of all the pages that are the logical pages that are they're currently valid in the process. So I hope this helps with a better understanding of how map pages work, and we'll hope to see you again for part 3. Thank you.